This video includes information on introduction to spontaneity and entropy.
Chapter 12 deals with thermodynamics. So we're going to kind of shift gears a little bit. And we're going to talk about a couple of the laws of thermodynamics. And the first law of thermodynamics is something that was talked about in Chem 1. So the first law of thermodynamics is also known as the law of conservation of energy. And that essentially means that energy can't be created or destroyed, or the energy in the universe is a constant. Now, even though the total amount of energy in the universe is a constant, it can switch forms, okay? It can change its forms during physical and chemical processes. And when we talk about the first law of thermodynamics, or the law of conservation of energy, it's a way for us to kind of bookkeep energy within a chemical or a physical change. It'll help us to answer questions like, how much energy is involved in a particular change? Or does energy flow into or out of a system? Or what form does the energy finally assume after a physical or a chemical process? Now we want to talk a little bit about spontaneity. And when we deal with a process that's spontaneous, it's one that occurs without any type of outside interference. It's going to happen on its own. It's spontaneous. Examples: heat always flows from hot to cold. That's a spontaneous process. It will never flow in the opposite direction. Or water will spontaneously freeze below 0 degrees Celsius. Okay, water can't melt below 0 degrees Celsius. Ice spontaneously melts above 0 degrees Celsius. So spontaneous processes are ones that occur without any outside intervention. Non-spontaneous processes are ones that have to be forced to occur. Okay, they're not going to happen unless there's something forcing it or driving that process to happen. And that would happen by some kind of input of external energy. A process that's spontaneous in one direction is usually non-spontaneous in the reverse direction. Now, when we talk about spontaneity, it does not mean the same thing as saying instantaneous. So processes that are spontaneous do not necessarily go fast. As an example, if we were to look at radioactive decay is a spontaneous process. And if we were to look at tactinium, which is used in medical imaging studies, it will decay very quickly. Okay, its half-life is about 6 hours. But if we were to look at uranium, uranium's half-life is much longer. Okay, uranium, although it takes a very long time to go through a radioactive decay, that decay process is still a spontaneous process. So just because something is spontaneous doesn't mean it's instantaneous, doesn't mean it happens quickly. Okay, diamond actually spontaneously changes into graphite over time. But it takes such a long period of time, it's such a slow process, that it would take the time of the universe in order to change all that diamond into graphite. Now, one of the things that determines spontaneity is the dispersal of matter and energy throughout a system. So spontaneity of a process is determined by the extent to which it changes the dispersal or the distribution of matter and or energy. A spontaneous process usually results in a more uniform distribution of matter or energy. So as an example, if we have substance X that's at a higher temperature and substance Y that's at a lower temperature, and we were to put X in contact with Y, energy is going to spontaneously flow from X to Y. And the reason it's going to do that is because that causes a more uniform distribution of thermal energy. Now, if we were to look at, let's say, two gases in a container, okay, and we have gas A in one container and we have nothing in the second container, and we open up the stopcock between those two containers, the process will spontaneously spread those particles out. We'll have a more uniform distribution of matter spontaneously. It's non-spontaneous that all of these particles are going to move back into here. So when we talk about spontaneity, it's a process that results in a more uniform distribution of matter or a more uniform distribution of energy. Let's look at these examples and just use your common sense. Are the following processes spontaneous or non-spontaneous? Think about what the term spontaneous means. Will the process that's listed take place on its own, or does it have to be forced to occur? So let's think about A. Liquid water freezes at a temperature below its freezing point. Would we expect that to be spontaneous or non-spontaneous? Spontaneous. That process is going to take place. We don't have to force it to happen. Liquid water freezing at a temperature above its freezing point. Spontaneous or non-spontaneous? Non-spontaneous. That's not going to happen on its own. The combustion of gasoline. Spontaneous or non-spontaneous? Okay, this one's a little bit of a trick. I agree that we have to start the gasoline combusting. We have to overcome what's called activation energy. But once we do that, once that gasoline has started to combust, do we need to force it to combust anymore? Think about that. No, we don't, right? So is the combustion of gasoline spontaneous or non-spontaneous? It's actually spontaneous, yeah. Now, again, we have to initiate the process. That's not what spontaneity is. Spontaneity is once it starts, will it keep going? Okay. And gasoline, once we ignite it, will continue burning. A ball thrown in the air. That ball is not going to go in the air unless we throw it in the air, right? Okay, so that's non-spontaneous. A raindrop falling to the ground. Is that going to happen on its own? It is spontaneous. Iron rusting in a moist atmosphere. Does that happen on its own? It does, right? Yeah, that's a spontaneous process. So again, the one that was a little bit tricky was the combustion of gasoline. You do have to get it started, but after you get it started, it's going to combust on its own. And that's what we mean when we talk about something being spontaneous. Will it continue on its own? So we want to introduce this term called entropy. Entropy is a thermodynamic property that relates the spontaneous heat flow accompanying in a process to the temperature at which that process takes place. So the letter that we're going to use to stand for entropy is an S. And in order for us to calculate an entropy change, we're going to take the heat that's flowing into or out of a system in terms of joules and divide it by its temperature in terms of Kelvin. So entropy is always joules per Kelvin. It's a state function. We've talked about state functions before. State functions are ones that don't depend on the pathway. So the change in entropy for a system will equal the final entropy minus the initial entropy. And entropy is an extensive property. It means that it depends on how much stuff we have. So entropy and the amount of matter we have are directly proportional. So let's go into a little bit about what entropy is, and we'll talk about it on a macroscopic scale, but then we're going to kind of boil it down to what it actually means. So when we talk about entropy, we need to talk about what are called microstates. Now, the symbol for microstates is a capital W. And it is a specific configuration for the locations of atoms in a system and the energies of those atoms in a system. So if we have 4 molecules that we have in 2 boxes, there are 16 different ways that we can arrange those 4 molecules in those 2 boxes, okay? All 4 molecules could be in the first box, or maybe all 4 molecules are in the second box, or maybe 3 molecules are in the first box and 1 molecule is in the second box, or maybe 1 molecule is in the first box and 3 molecules are in the second box. Or maybe 2 molecules are in each box. Different ways that 4 molecules can be arranged in 2 boxes. Now, if we were to talk statistically, the most likely outcome is the one that has the highest number of equivalent microstates. So in this case, statistically, it's much more likely that 4 molecules will be distributed so that 2 molecules are in each of the 2 boxes in our system. Probabilities, and we're not going to go into a whole lot on probabilities. That's for another class. But when we look at a system that contains capital N, number of particles distributed in lowercase n, boxes, the total number of microstates or the total number of possible ways that those particles can be arranged is n to the nth power. So in this case, lowercase n is the number of boxes, which is 2. Capital N is the number of particles, which is 4. So 2 to the 4th power equals 16. So there are 16 different ways that those 4 particles can be arranged in 2 boxes. Probability-wise, if these are the 16 possible combinations, we have a 1 in 16 chance that all 4 particles are going to be in the first box. And we have a 1 in 16 chance that all 4 particles will be in the second box. It's the lowest probability of all the different combinations. There are 6 16ths of a chance that the particles are going to be arranged like this. It's the greatest probability. Now for B and D, they're both a 4/16 chance. So not the least probable and not the greatest probable. For this 2-box system, the number of possible arrangements increases exponentially as 2 to the n power. So for the example that we looked at before, we had a 2-box system and we had 4 molecules that we needed to arrange in those 2 boxes. But let's say we were talking about a mole of particles. If we had a mole of particles and we were arranging them in a 2-box system, it would be 2 raised to Avogadro's number, or 6.02 times 10 to the 23rd, which is an extremely large number. So entropy is the thermodynamic function that describes the number of energetically equivalent microstates that are available to a system at a given state. Okay, how do we calculate entropy? So S is our symbol for entropy. K is a constant. It's just a proportionality constant. And W is our number of microstates. Now, K is a constant. So it's 1.38 times 10 to the negative 23rd joules per Kelvin. So that number always goes in here. Now, ln is a function on your calculator. Okay, it's the natural log function on your calculator. Now, every calculator is different. For many calculators, it's the button right below the log button. You're probably a lot more familiar with where the log button is on your calculator, and we're going to use that a lot later on in the course. But you want to find the ln button. That's the natural log button, and that's what we'd be using in this kind of calculation. So the entropy of a set of equivalent microstates is related to the number of microstate options we have. So what does that really mean? That's a lot of words. It's really hard to maybe comprehend. When we talk about entropy, essentially entropy is the measure of the randomness or the disorder in a system. And nature tends to go towards more disorder. Okay, that happens spontaneously. Ideal example, okay, this is like the classic example that's given to kind of give you an idea of what we mean when we talk about entropy. Think about your bedroom and how, I know when my kids were growing up, Sunday afternoon, part of our weekly routine was they needed to, go in and straighten up their room. They needed to put their laundry away and clean up their room and get ready for the week. Okay, and that takes energy to get everything organized, to make everything ordered. But it seems that by the time they wake up Sunday morning or Monday morning, particularly my daughter, not as much my son, by Monday morning, her room is a total mess again. Okay, and the reason for that is nature tends to go towards disorder. Nature tends to be sloppy. It takes an input of energy in order to keep things nice and orderly. And entropy is a measure of the randomness or the disorder of molecules in a system. So when we want to calculate how much the entropy or the disorder or the randomness of a system changes, we could take the measure of the final entropy and subtract the initial entropy, since it's a state function. And we know that we can calculate entropy by taking this proportionality constant times the natural log of our microstates. So K times the natural log of the initial or the final number of microstates minus K times the natural log of the initial number of microstates. Or we can take this and combine it together and say K times the natural log of the final number of microstates divided by the initial number of microstates. If the final number of microstates is greater than the initial number of microstates, the entropy in the system increases. And delta S will be a positive value. The system's becoming more random or more disordered. If the final number of microstates is less than the initial number of microstates, then the entropy of the system, the randomness or the disorder of the system, will be decreasing, and delta S will be a negative value. And we're just talking about it in terms of the molecular level and the probability of the way that those molecules are going to be arranged within the system. Now, we can talk about microstates with respect to particles, like we did in our first example. We can also talk about it in terms of heat. So let's say that we have 2 units of heat, and we'll use a little asterisk for our heat, that's distributed in 2 boxes, each containing 2 particles. Okay, so what would we have? Well, this is one set of possibilities where all of the energy is in the first box. Now, maybe the energy is attached to the first molecule, or maybe some of it's on the first molecule and the second molecule, or maybe all of it's on the third molecule, but all of the energy is in the first box. Or maybe we have something like C, where all of the energy is in the second box, either on molecule C, or on C and D, or just on D. But the third possibility for the way that that energy can be distributed in this particular system is if some of the energy is in the first box and some of the energy is in the second box for all of our different concentrations. So the most likely outcome would be the one where the heat or the energy is evenly distributed within that particular system. So let's look at a couple of questions where we have to do some calculating. So if you don't have your calculator out, grab your calculator. So let's say that we want to calculate the change in entropy associated with the processes below. So we're going to look at 2 of them. So for our first one, we have 4 particles and we have 2 boxes that they can be distributed in. And they're going from this initial state here to this state here. Well, this has only 1 microstate, whereas this one has 1, 2, 3, 4, 5, 6 different microstates. So to calculate the entropy change, we would take K times the natural log of the number of microstates we have finally at the end, divided by the number of microstates we had initially. So WF would be 1, 2, 3, 4, 5, 6, whereas WI would be just 1. So K is a constant. It's always 1.38 times 10 to the minus 23 joules per Kelvin. And we're going to multiply that by the natural log of 6 divided by 1. So the natural log of 6. So I do want you to plug that in your calculators. I want to make sure that you know how to plug it in your calculators. So 1.38, instead of using this times 10, use that EE or that EXP button on your calculator. Don't plug in times 10. So 1.38 EE negative 23 times the natural log ln of 6. Plug that into your calculators. I want to make sure that your calculator helps you and isn't a hindrance. So 1.38 EE negative 23 times ln of 6. And plug your answer that you get into the calculator. Let's see what you get. Agreed. Good. So I'm getting 2.47. Now I'm not going to write E because that's kind of calculator language. So I'm just going to put the times 10 back in there. But 2.47 times 10 to the 23rd joules per Kelvin. Now, the important thing about this, besides the number itself, is that it's a positive number. And if delta S is a positive number, it means we're increasing the entropy of the system. We're making the system more random or more disordered than it was to begin with. And at the beginning, there was only one way that those particles were arranged. After the change, there were 6 ways that it was arranged. So we're increasing the entropy of the system because we're increasing the number of microstates. So let's look at this one. Okay, we're looking at heat, but it doesn't really matter. Okay, it's just how many microstates do you have finally, and how many microstates do you have initially? So initially we have 1, 2, 3 microstates. Okay, the energy is all in the first box, 3 microstates. The final microstates are 1, 2, 3. But this time, all the energy is in the second box. So we're going to use our equation. Okay, K is a constant, so it's 1.38 times 10 to the minus 23. Think about what WF is and what WI is, and calculate what your change in entropy would be. And just plug it into the chat there so we know we got it done. Okay, so we're going to be taking 1.38 EE negative 23 times the natural log of 1. But the natural log of 1 is 0. And anything multiplied by 0 is 0. So there's no entropy change. Think about that. The energy was all in the first box. And now it's all in the second box, but the number of microstates we had to begin with is the same as the number of microstates we had at the end. So we're not changing the order or the randomness of that energy. So our delta S value is 0. Now, the most probable distribution is the one that's going to have the most uniformly dispersed or distributed energy or matter. A spontaneous process where the energy is uniformly distributed yields an increase in energy. So if we are increase in entropy. So if we had box X which is at a higher temperature, and we have box Y, which is at a lower temperature, and we put those two boxes in contact with each other, the energy is going to evenly distribute itself. Energy is going to move from high to low. And it's going to do that to evenly distribute or disperse that energy. The energy isn't going to flow in the opposite direction. And the energy is going to continue to flow from X to Y until both X and Y are at the same energy, until the energy is evenly distributed. And when we talk about particles, particles are going to be doing the same thing. So if we have a gas in a container, and they're separated, so there's nothing in this container and all the gases in this container, and then we were to open the stopcock, these molecules are eventually going to spontaneously, evenly distribute themselves between those two containers. It's not spontaneous that all the particles are going to go back over on this side. Matter tends to be uniformly dispersed or uniformly distributed. When we talk about entropy, the standard entropy of a substance is the energy dispersed into 1 mole of that substance. It depends on several things. One of the things it depends on is what's the physical state of the substance. Is it a solid? Is it a liquid? Or is it a gas? So if we were to look at solids, solids have the least entropy of our 3 states because the particles are in a fixed position. But if we melt that solid into a liquid, we're going to be increasing the entropy of the system. Delta S is positive when we melt a solid. There's more microstates, more places that these particles can be arranged in a liquid state than in a solid state. And if we were to take a liquid and boil it, now we've increased the entropy even more. So delta S will be positive when we melt a solid and positive when we boil a liquid. But the reverse, if we were to condense a gas or freeze a liquid, the entropy decreases and delta S would be a negative value. Now, objects at higher temperatures also have higher entropies, even if their phases don't change. So if we wanted to look at a graph of entropy versus temperature, and we start down here at 0, as we increase the temperature of the solid, the entropy of the particles increases a little bit. The particles have a little bit more freedom to move as the solid becomes warmer. But when the substance reaches its melting point, this point here, the substance is changing from a solid to a liquid, and the entropy increases a lot because we're breaking some intermolecular forces, and the particles are going to be more random. If we have a liquid and we warm up that liquid, the entropy in that system increases a little bit as we add more energy in until eventually we get to the boiling point. And now the energy that we add in causes that substance to change from a liquid to a gas, and we increase that entropy greatly. And then if we were to increase the temperature of a gas, that entropy would increase again. Now, another thing that determines the entropy of a particular system is the molar mass of the particles that make up that system. If we were to look at a particular system and we're not changing the state of that system, heavier elements have a greater entropy than lighter elements. Okay, another factor that's going to affect entropy is the complexity of the molecules. And in general, when molecules are more complex, they're going to have higher entropies than molecules that are simpler. So if we were to look at a molecule, there's lots of different ways that those molecules can move. Okay, the bonds can move. So when we look at a molecule, the more atoms that are there and the more bonds that form, the greater the entropy or the more microstates those molecules in that system can have. Now, if we were to look at what are called allotropes, okay, something like diamond and graphite, they're both carbon, but the way that the carbon atoms are arranged is slightly different. Okay, the less constrained structure has a higher entropy. If we were to look at diamond, the carbon atoms in diamond are in a much tighter fixed position than they are in graphite. So graphite has a higher entropy than diamond does. So when we talk about entropy, we just mean, how disordered are the particles. If we increase the disorder, we're increasing the entropy. If we decrease the disorder, we're decreasing the entropy. The last factor about entropy is when we talk about mixtures. If we were to look at two substances before they're mixed together, and then after we mix them together, they'll be at a higher entropy after they're mixed together because the particles are freer to move around in the solution than they were when they were separate. So generally speaking, like if this was our solute particles and this was our solvent particles and we mix them together, there's a lot more ways that the solute and solvent particles can be arranged in the solution. So the entropy is increasing. So mixtures have a higher entropy than the substances they were made from. Okay, so if we were to look at sodium chloride, which is a crystalline solid, there's a very low entropy disorder in a crystal. But if we were to take that sodium chloride and dissolve it in water, the sodium ions and the chloride ions get pulled apart. They become evenly distributed in the solution, and we increase the randomness or we increase the disorder of those particles. They can move around more. They have more microstates and their entropy increases. So dissolving has a positive delta S because the entropy is increasing. If we were to precipitate a solid out, our delta S or our entropy would be going down. It would be a negative value. So let's do a little bit of practice. There isn't going to be math involved yet. It's just kind of concept. We want to decide what the sign on delta S is for the following. So delta S is entropy. If entropy increases, delta S is positive. And if entropy increases, we're looking at something that becomes more random. The particles are more random. If delta S is negative, then the entropy is decreasing. So the particles are less disordered, or the flip side of that would be they're more ordered. Okay, so let's talk about the evaporation of alcohol. So think about what's happening when alcohol evaporates. It goes from a liquid to a gas. So in the chat, you could just put a plus sign or a negative sign if you want. What would you expect, or positive or negative? What would you expect the sign to be? Yeah, agreed. I would expect the sign to be positive because particles in the gaseous state are more disordered than particles in the liquid state. Okay, so let's look at freezing water. So think about what state we're starting at, what state we end up with, and what you would expect to happen. Yeah, negative, right? We're going from a liquid to a solid. The particles in that sample are becoming less disordered. So your value would be negative. All right, compressing an ideal gas at a constant temperature. Agreed, negative. Okay, think about that. An ideal gas, if we were to compress that ideal gas at a constant temperature, the pressure is increasing, the volume would decrease. If the particles have less places to be, they're becoming more ordered as they become compressed. And in fact, if we compress an ideal gas enough, it would become a liquid. And we could even compress it enough to make it a solid. So yeah. Okay, heating an ideal gas at a constant pressure. Okay, good. If we heat an ideal gas at a constant pressure, increasing temperature increases the volume. If we increase the volume, there are more places for the particles to be. They're more random. So the entropy is increasing. It's positive. Dissolving potassium chloride in water. Positive. Yeah. Again, potassium chloride in its crystalline state has a very low entropy, but if we dissolve it in water, those ions are free to float around more. They're going to be more disordered. All right. So now let's look at some chemical processes. So calcium carbonate decomposes into calcium oxide and carbon dioxide. The key to that is look at the states of matter. Look at what you start with and look at what you end with. And what would you think happens to the disorder in the system? Yeah, it's going to be positive. We're starting with a solid, but we end up with a solid and a gas. And the gas has a much lower entropy than the original solid had. So our entropy is increasing. It's going to be positive. Now, the next one doesn't help as much because we're starting with gases and we're ending up with a gas. So there's no phase changes. That makes it a little bit harder. But let's think about this. We're starting with, well, two different gases and we're ending with one gas. Plus, we have 2 + 1. We have 3 moles of gas to begin with and 2 moles of gas at the end. So we're becoming more ordered or more disordered. If we start with 3 moles of gas and we end up with 2 moles of gas. Yeah, I don't think that's right. 3 moles to 2, that should be negative. That should say negative. Oops, that's not right. We're going from 3 moles of gas to 2 moles of gas. It's becoming less disordered. That should be a negative. That's not right. Okay, let's look at the last one. We've got 2 moles of liquid. What about oxygen? The question was. So we've got 2 moles of sulfur dioxide and 1 mole of oxygen. So we have 3 moles of gas originally. We only have 2 moles of gas at the end. So this should be negative. So look at this one. Okay, good. Sorry about that. So we've got 2 moles of liquid, 15 moles of gas. We end up with 6 moles of gas and 3 moles of liquid. What do we think's happening there? Really, let's just focus in on the gas for a second. Do we think the entropy is increasing or do we think the entropy is decreasing? Oh, it says positive again, and that should be negative. Geez, what was I putting in there? I don't know what I was putting in there. That should say negative. Sorry about that. Because we're going from 15 moles of gas to 6 moles of gas. So this should say negative and this should say negative. I think I was being happy with my copy and pasting and I copied and pasted the wrong things. So this should be negative. This should be negative. Sorry about that.